Somewhere inside a Google lab this year, a quantum chip did something that took a supercomputer 13,000 times longer to even attempt. Not in theory, not in a simulation. On real hardware, solving a real problem and getting verified by scientists who tried desperately to prove it wrong. Meanwhile, on the other side of the world, engineers were teaching artificial intelligence to calibrate quantum machines in real time, correcting errors before they even happen. Two of the most powerful technologies on Earth just started feeding each other, and if you are not paying attention to this collision right now, you are about to miss the biggest shift in computing since the smartphone. For years, quantum computing has felt like a promise that keeps getting pushed back. Every headline said the future was close, and every follow-up article quietly admitted it was still years away. That pattern defined the entire field for nearly 2 decades. Quantum supremacy was declared, then debated. Roadmaps were announced, then extended. Investors got excited, then cautious, then excited again. It became almost a running joke among engineers that quantum computing was, and always would be, 10 years away. Something changed in 2026, not because one single company suddenly cracked the code, but because multiple breakthroughs from different teams landed at roughly the same time, and they started reinforcing each other. That convergence is the real story here, and it is a story with 2 halves. One half is quantum computers getting good enough to genuinely help artificial intelligence. The other half is artificial intelligence getting good enough to genuinely help quantum computers. Put those 2 halves together, and you get a feedback loop that experts are now calling quantum AI. Let's start with the headline-grabbing part, because it deserves the attention. Google's quantum chip, known as Willow, ran an algorithm called quantum echoes that measured something called out-of-time order correlators roughly 13,000 times faster than the best possible estimate using classical supercomputers. This was not some obscure academic exercise either. The algorithm has real-world application in mapping molecular structure, using data drawn from nuclear magnetic resonance. In simple terms, this quantum chip helped reveal the physical shape of a molecule in a way that would have taken a classical machine dramatically longer to figure out. And what makes this result different from earlier quantum milestones is something called verifiability. Back in 2019, Google claimed quantum supremacy with a benchmark that was almost impossible for outsiders to independently confirm. It sparked debate for years. This time, the quantum echoes result was designed so other quantum machines of similar quality could reproduce it. That reproducibility matters enormously in science. It is the difference between a claim and a demonstrated fact. Of course, not everyone accepted the comparison quietly. IBM pushed back, arguing the same task could theoretically be simulated on its own Summit supercomputer in roughly 2.5 days, rather than requiring 13,000 times longer. That disagreement is worth mentioning because it shows this field is still fiercely competitive and companies are not simply taking each other's word for it. Healthy skepticism between rivals is often a good sign. It means claims are being stress tested rather than accepted on faith. While Google was chasing precision, IBM was chasing scale using a completely different philosophy. Instead of building one enormous chip, IBM has been connecting multiple smaller quantum processors together into a unified system, an approach the company calls quantum-centric supercomputing. By May of 2026, IBM had successfully interconnected several of its Flamingo processors, creating a modular system with roughly 4,000 qubits acting together as a single logical unit. Think of it less like building one giant brain and more like networking many smaller brains so they think as one. If that architecture continues scaling successfully, it could offer a very different and potentially faster path toward large-scale quantum computing than trying to cram everything onto a single chip. Underneath both of these approaches sits one of the most important, least glamorous problems in the entire field: error correction. Quantum bits, or qubits, are incredibly fragile. They lose their delicate quantum state at the slightest disturbance, a process called decoherence. For decades, this fragility was the single biggest obstacle preventing quantum computers from running long, complex calculations reliably. Google's Willow chip demonstrated something researchers had theorized about for nearly 30 years, but never actually achieved outside of theory. As they increased the size of their error-correcting code from a smaller grid of qubits to a larger one, the error rate actually went down instead of up. Scientists call this crossing the threshold, and it is a genuinely enormous deal because it proves that a reliable, large-scale quantum computer is not just theoretically possible, it is physically achievable using real hardware. This is where artificial intelligence quietly enters the picture, and this is honestly the part most casual coverage completely misses. Building and running these delicate quantum systems requires constant, extremely precise calibration. Pulse sequences controlling the qubits need to be adjusted continuously to compensate for tiny amounts of drift and noise. Historically, this calibration work was done using traditional control systems, and painstaking, Manual tuning by physicists. Increasingly, companies are turning to small, specialized machine learning models to handle this job instead. These models monitor the quantum hardware in real time, predict where noise is likely to occur before it actually happens, and adjust the system automatically to compensate. In other words, artificial intelligence is now helping keep quantum computers stable enough to function at all. This is the quieter, arguably more mature half of the quantum AI story. While headlines chase dramatic speed-up numbers, a huge amount of practical progress is happening in error correction decoders, noise modeling, and hardware calibration, all powered by machine learning working behind the scenes. Researchers at companies like Riverlane have pointed out that quantum error correction made a genuine leap from theoretical concept to tangible hardware implementation over the past 2 years, and machine learning played a significant supporting role in that transition. This is not the flashy side of the story you see in viral headlines, but it might be the side quietly doing the most real work. Now, let's flip the relationship around and look at how quantum computing is starting to help artificial intelligence, because this direction is newer, more speculative, and honestly, more contested among experts. Quantum computers are naturally well suited to certain kinds of optimization problems, essentially finding the best possible answer among an almost incomprehensibly large number of possibilities. In machine learning, that translates into a few very specific, very practical applications. One is hyperparameter tuning, the process of finding the ideal settings that control how an AI model learns, things like learning rate and batch size. Traditionally, this requires expensive, time-consuming search methods. Quantum processors show early promise in exploring those enormous search spaces more efficiently. Another application is feature selection, figuring out which variables in a massive dataset actually matter. A task that becomes computationally brutal once you are dealing with thousands of variables at once. Earlier this year, a research paper describing something called quantum-enhanced neural architecture search made waves in specialist circles, without getting nearly the mainstream attention it probably deserved. The idea is that quantum processors could help design better neural network structures themselves, essentially using quantum computing to help build better artificial intelligence from the ground up. It is technical, it is early stage, and it is exactly the kind of unglamorous breakthrough that tends to compound quietly until it suddenly becomes impossible to ignore. Here is where I want to pump the brakes a little, because a responsible breakdown of this topic has to include the skeptics, and there are serious ones. Some of the most respected voices in quantum machine learning research have explicitly pushed back against breathless claims that quantum computers are about to revolutionize how large language models get trained. Researchers closely tracking the field have called certain proposed exponential speedups in quantum machine learning speculative at best, and they have pointed out that the genuinely defensible quantum advantage right now lives in a narrower space, specifically in problems with deep structural or algebraic complexity that classical computers cannot easily fake or approximate. That is a very different, much more modest claim than the sweeping statement that quantum computing is about to reinvent artificial intelligence overnight. Even within the industry itself, there is real disagreement about timelines. NVIDIA's Jensen Huang initially offered a fairly conservative estimate, suggesting truly useful quantum applications might be 15 to 30 years away, before later softening that position. Bill Gates, on the other hand, has offered a noticeably more optimistic 3 to 5 year window for practical utility. When two of the most influential figures in technology disagree by literally decades on the same question, that tells you this field is still full of genuine uncertainty, not settled consensus. Anyone presenting a confident, specific timeline as guaranteed fact is oversimplifying a genuinely complicated situation. There's also a serious security dimension to all of this that deserves real attention because it is not just an academic curiosity. Sufficiently powerful, fault-tolerant quantum computers could eventually break widely used encryption standards, including the RSA, encryption protecting huge portions of the internet's sensitive data today. Recent research suggests that breaking RSA encryption might require roughly 1 million logical qubits, a number that has actually been revised downward from earlier estimates closer to 20 million, thanks to improvements in error correction efficiency. That is still an enormous engineering distance away from what current hardware can achieve, but governments are not waiting around to find out exactly when that threshold gets crossed. International groups have already begun mandating post-quantum cryptography standards, specifically because adversaries are believed to be harvesting encrypted data today with the explicit plan of decrypting it later. Once sufficiently powerful quantum machines exist, this threat even has a name in security circles: harvest now, decrypt later. It helps to understand why error correction is treated as such a make or break issue in this field, because the concept itself is not intuitive at first glance. A single physical qubit is extremely unreliable on its own. It can flip its state, or lose coherence from something as small as a stray cosmic ray, or a tiny vibration in the surrounding equipment. To get around this fragility, engineers combine many physical qubits together into what is called a logical qubit, using redundancy to protect the underlying information the same way a hard drive might store backup copies of important data. The problem is that historically, adding more physical qubits to build a bigger logical qubit also introduced more opportunities for errors to creep in, meaning the system got noisier as it got bigger. Google's below-threshold result matters because it proved the opposite pattern is achievable. As they scaled their error-correcting code upward, the logical error rate actually dropped, cutting roughly in half with each step up in size. That is the mathematical signature everyone in the field had been waiting decades to see confirmed on real hardware, not just in theoretical simulations. To put the scale of the remaining challenge in perspective, current estimates suggest that a fully fault-tolerant quantum computer capable of tackling genuinely difficult, commercially valuable problems will require processors containing anywhere from tens of thousands to potentially millions of physical qubits. Today's most advanced chips are still measured in the hundreds. IBM's Nighthawk processor, for example, contains around 120 physical qubits, which researchers estimate might support only a handful of fully fault-tolerant logical qubits once error correction overhead is accounted for. That gap between where the hardware sits today and where it needs to be for broad commercial usefulness is exactly why serious researchers keep emphasizing that 2026 validates the underlying path forward rather than completing the actual journey. There is another layer to this story worth exploring, and it involves a completely different kind of qubit technology entering the picture. Google recently added neutral atom hardware as a second modality alongside its existing superconducting qubit chips, a strategic decision explicitly designed to address what researchers describe as a space-time trade-off. Superconducting qubits, the technology behind Willow, tend to scale well when it comes to circuit depth, meaning how many sequential operations you can perform before errors accumulate too much. Neutral atom arrays, by contrast, tend to scale more easily in terms of raw qubit count. By pursuing both approaches simultaneously rather than betting everything on one architecture, Google is essentially hedging its bets on which path proves more practical for building that eventual million-qubit machine everyone in the field keeps referencing as the ultimate long-term target. Meanwhile, competitors like Quantinuum and IonQ have been pursuing trapped ion technology, a third distinct architectural approach with its own trade-offs around gate fidelity and scaling speed. Oxford Ionics reported achieving 99.99% fidelity for 2-qubit gate operations, an extremely high precision benchmark that demonstrates just how mature certain corners of this technology have become, even while the overall industry still works toward practical large-scale deployment. Watching multiple architectures mature in parallel, rather than a single winner emerging early, suggests the field genuinely has not settled on one best approach yet, and that kind of open competition tends to accelerate overall progress rather than slow it down. It is also worth pausing on how researchers are now trying to measure progress in this field, because the old metrics are starting to show their limits. For years, the go-to-headline number was simply qubit count. How many qubits does a given processor contain? But raw qubit count on its own tells you very little about whether a system can actually do anything useful, since noisy, error-prone qubits are far less valuable than fewer, cleaner ones. Some researchers have proposed a new measurement framework built around something called QOPs, designed to function similarly to how mobile network generations get labeled, moving from kiloquops to megaquops to eventually gigaquops and teraquops as the technology matures. The idea is to create a clearer, more honest way of tracking real computational capability rather than getting distracted by vague marketing claims about quantum advantage. Expect this kind of more rigorous benchmarking language to become increasingly common as the industry matures past its early hype-driven phase. There's also a fascinating research thread connecting quantum computing directly to how artificial intelligence handles chaotic, unpredictable systems, the kind of messy real-world data that classical machine learning models often struggle to model accurately. Scientists have recently demonstrated that blending quantum computing with artificial intelligence can meaningfully improve forecasting process. Chaotic systems show up everywhere in the real world, from weather patterns to financial markets to the turbulent behavior of fluids, and even modest improvements in how well we can predict them carry enormous practical value. This is other on problems classical computing alone has historically found frustratingly difficult. None of this progress is happening in a vacuum either. Quantum computing investment has been broadening beyond the portfolios, run more accurate risk simulations, and design more efficient supply chains. These pilots remain narrow and experimental. Companies do not typically commit real budget toward emerging technology unless they see a credible near-term path toward measurable value, even if that value is still modest today compared to the eventual promise. If you're finding this breakdown useful, go ahead and hit that subscribe button. Because we cover stories exactly like this every single. So where does all of this actually leave us heading into the rest of 2026 and beyond? The most credible experts in the field seem to be converging on a similar message, even if they disagree on exact timing. This year represents what some are calling quantum general purpose, quantum computing capable of solving arbitrary problems better than. The next major milestone experts are watching closely is what Google calls a long-lived logical qubit, essentially proving that error-corrected quantum information can be preserved reliably over much longer periods of time. If that milestone gets reached on institutions sometime around early 2027, that is a real, specific, checkable prediction, not vague hype, and it is worth watching closely over the coming months. What ties this entire story together is that feedback loop we mentioned earlier, and it is worth sitting with for a moment because it is genuinely a new kind of technological relationship. Better artificial intelligence helps physicists design better quantum hardware through improved simulation, better calibration, and smarter error correction. Better quantum hardware, in turn, has the potential to eventually help train better artificial intelligence models faster and with less energy once the technology matures past today's narrow use cases. Two technologies, each accelerating the other, locked into a genuine feedback loop rather than simply existing side by side. That kind of compounding relationship is exactly the pattern that tends to precede major unexpected leaps in technological history. None of this means you should expect science fiction level quantum AI systems solving every problem on your desk by next year. The honest, grounded reality is that 2026 marks a genuine inflection point, not a finish line. Error correction crossed a critical theoretical threshold and proved it works in practice. Modular quantum architectures demonstrated real scaling potential. Artificial intelligence quietly became essential infrastructure for keeping quantum systems stable, and narrow but genuinely useful. Applications in chemistry and materials, science started delivering results that classical computers simply could not match, verifiably and reproducibly. Whether you are a developer, an investor, a student, or simply someone trying to understand where technology is actually headed rather than where headlines claim it's headed, this is the moment to start paying attention, not because quantum AI has fully arrived, but because the foundation just got laid in front of everyone, mostly without the mainstream fanfare it probably deserved. The organizations and individuals building literacy in this space right now are positioning themselves years ahead of everyone who waits for the technology to become obvious and unavoidable. Quantum computing spent 2 decades being the technology that was always almost here. In 2026, for the first time, multiple independent teams proved specific, verifiable, reproducible pieces of that promise on real hardware, while artificial intelligence quietly became the tool making those very systems stable enough to function. That is not hype. That is not a marketing slide from a startup trying to raise its next funding round. That is a documented, contested, occasionally messy, but genuinely real shift happening in laboratories and data centers right now, and it is only going to accelerate from here. If you want to keep following where this goes next, make sure you like this video and subscribe so you don't miss the follow-up, because the next 12 months in this space are going to move faster than almost anyone outside the field currently expects.